a magnetic monopole, but we know magnets are dipoles, so it would be impossible to make a monopole, so the answer is D. So now it's the oil drop experiment. So if it's asking what's the electrical force, and you have charge, so Q, and you have E, so you know F equals EQ, so you just multiply them and you should get B. So question 3, there's 2 different plates, and we know to find the electrical field, it would be E equals V on D. But this time they're asking to find V, so just rearrange it, and you sub in E is this one, and D is 5 millimeters, but you have to convert that to meters because of SI units, and you should get A. So there's a step-down transformer going from 240 volts to 12, and we know that V2 on V1 is equal to N2 on N1. So it's 240 divided by 12 is going to be 20 on 1, so that means N2, it should be 12 on 240. So it's going to be 1 on 20, so that means N2 is 1, and N1 is 20, so that would be D. So now there's, following on from the same question, because it applies to question 4 and 5, they're delivering 48 watts to a resistor, and the transformer is ideal, so that means power before the transformer is the same as after. So what gives the peak current on the secondary coil? So on the secondary coil, we know power is 48, and we know that voltage is 12. So that means current is going to be power on voltage, which is 12. And then it's asking for peak current. Oh, sorry, this is 4. And then peak current, but we know this is not peak current, so we have to multiply it by root 2, and you should get 5.7. So now we have magnetic flux, and we're looking for EMF. You can easily see the answer is going to be D, because EMF is the gradient of the flux graph, and the gradient would be straight lines and horizontal straight lines, and the only one that has that is D. So yeah, it's pretty simple. So now we have a model car, which is 2 kilograms, and there's a horizontal force of 4 here. And then what's the magnitude of acceleration of the car? So F equals ma, and then just 4 divided by 2 is 2, so it's C. So what's the magnitude of the impulse? So impulse in the first 5 seconds, so impulse is delta F, F on delta T. So the force is 4, and delta T is, the force is not 4. And delta T is 5, and the force is 4 times 2, so that's, my bad, I'm using the wrong equation, sorry. F times delta T, so 4 times 5, which is 20. So same rocket, the car accelerates from rest for 10 seconds. So what's the final speed? So for this one, you can use your constant acceleration formulas. So U is 0, T is 10, and A is 2, because we figured that out from this question. And then V, we're looking for the equation that doesn't have S, so we can use V equals E plus AT. So it's going to be 0 plus 20, which is just 20. So question 10 is the train experiment. I don't know if there's a name for it, but basically it's the one where like a constant speed and velocity of 0 will have the same observations, but if you're accelerating, there was the example of the handles in the train, where if it's accelerating this way, then these move backwards. So using that example, we can see that the results when it's accelerating would be different from when it's in uniform motion. So the answer is B. So the sun emits this much energy for each second from radiation. And then what's the mass? So we can just use E equals mc squared here and let E equal 3.8 times 10 to the 26 divided by c squared, because we're trying to find m, and you should get B. In another question, they might have changed the each second part, but this time they kept it the same. So we don't have to do anything to this energy value. Oops. Like, for example, if they had asked, like, what mass do you lose each, like, minute or something, would have had to multiply this by 60. So just, like, being careful when we read the question. So what's the estimate of the spring constant? So on a force times extension graph, it would be the gradient. So the easiest points to look at, I think, would be the endpoints. So if you're looking at rise over run, it's just 400 on 1. So it's just C. And what's the initial kinetic energy of the car? So it's asking for kinetic energy. So we can't just find the area under the graph because that's spring potential for the whole time, but it's asking for initial kinetic energy. So we know that energy is conserved. So if we're looking for the initial kinetic energy, then one thing we can look for is the final energy, which would be when the car comes to rest. So the only other energy there would be ES. And when it's at the end, it's compressed at 0.5 meters. So meters, yeah. So you can just find half kx squared from there, only up to that point, because that's the end energy, and we want it to be conserved. So it's that, and then if you simplify it, you should get 50. So now this question is about diffraction. So it's asking why the teacher can hear the sound but not see the students. So A is completely wrong. Nothing is greater than the speed of light, and B is also wrong because again it's much less. So C, sound diffracts because it's smaller. No, that's not why. And D, it's because it's comparable. Yeah, that's correct. So there's a police car coming towards Lee, and then it continues on. So when it's coming towards her, the waves, because the velocity from the car is moving towards her, like the distance between the waves gets smaller. So then that causes her to hear them at a higher frequency. And then when it's moving away, then the distance between the waves is getting larger. Sorry, this is a bad diagram, but so that means it's going to be a lower frequency when it moves away. And that's why the answer is A. It's not going to be D, because D is technically correct for what the car is emitting, but it's asking for what she's hearing. So that's why D is wrong. So this one's about Heisenberg's uncertainty principle. And we know the slit here was introduced to lower the uncertainty in where the beam is going through. But because we've lowered the uncertainty there, the momentum in the y direction is going to increase because we can't have low uncertainty for both of these things. So the answer that corresponds to this is B. So quantized energy levels, this is kind of like that short answer question at the end of every test before this, but the answer is D, because we know discrete quantized energy levels are explained by standing waves that electrons form around atoms. So this one's about scientific methods. So it's asking about accuracy and precision. So we know accuracy is if you get the right value. So accuracy would be whoever gets this one, and precision would be whoever has values that are really close to each other. So you can see that neither Rob nor Jan are precise because all of their measurements have a high range. So Rob's range would be 0.4 between the 5 between the highest and lowest, and Jan's range would be to 0.16. So Jan is more precise than Rob, but you can see that Rob's actually achieved the true value. So he's got the correct measurement. And that means Rob is accurate, but he's less precise than Jan. So if we check with the answers, A is correct. B is not, because we know that Jan was not accurate, and we know Rob is less precise, and we know that they are not equally precise because the range is different. So which describes a hypothesis? So a possible explanation, yeah, that makes sense. An explanation that's been supported. That's not really a hypothesis. That's more of like your supporting background information or something. Again, same thing with C. And an explanation that's mathematically correct is also not true, because a hypothesis is what we're testing. So none of these three kind of say that that's what we're testing. So systematic and random errors. So systematic errors are ones that are built into your instrumentation or something. You can't really get rid of them, and they affect every one of your readings. Random errors are things that may happen once or twice, and it's not known whether they increase a value or decrease a value. So random errors can be reduced by repeated readings. Yes, that's true, because once you get the average of a bunch of readings, then it lowers the effect of a random error. So both random and systematic errors can be reduced by repeated reading. That's not true, because systematic errors occur in every reading. So even if you get the average of all the readings, then since each of them still has an error, then the average will also be an error. Whereas with random errors, say only this one had an error. So if we get the average of this, the averaged value will have it'll be less affected by the error because it's included the readings that haven't been affected. So systematic errors, yeah, C is wrong for the same reason as B, and neither can be repeated. No, that's not true, because random errors can be reduced by repeated readings. So that was multiple choice. So now we have an electric field, and it's asking what's the resultant field at X. So we know in electric fields, the field lines go from positive charges to negative charges. So at X, you can clearly see it's going to go to the left. So we have an electron in the ground state. So it's not excited, in an excited state. And it's going at a radius of picometers, and show that the force between the proton and the electron is this, and they've given you K, and they've also given you the charge. So we know that F is equal to EQ. We use this for one of the multiple choice. But since we don't have E, we have to expand it to K, Q1, Q2 on R squared. Actually, you could probably skip this step. So if we get K, which is 9 times 10 to the 9, Q1 and Q2 are the same, so I just wrote 1.6 times 10 to the negative 19 squared on R, which they have given us in meters squared again, and then just F equals 8.2 times 10 to the negative 8, which is what's required, so we know we have the correct answer. But always check this in your CADs, don't go straight to this step in case this doesn't actually turn out to be the answer. So now they want us to use this value and to calculate the speed. So we know around the circular path. So if it's a circular path, we know we're going to be dealing with centripetal motion. So the equation for that is F equals mv squared on R. And we have F, and we want V. So if we rearrange this, we get Fr on M square root. So that means V is F, so 8.2 times 10 to the 8 times R, which was 53 times 10 to the negative 12 on M, which they have given us is 9.1 times 10 to the negative 31. And that comes out to 2.2 times 10 to the 6. In the answer report for this year, I think they were cracking down on significant figures. So the lowest amount you can see is 2, because you have 2 here and 2 here. And the other value we used was this one, which was also 2. So 2 significant figures. So 2.2 times 10 to the 6. So now we have a motor, it's DC. And it's asking for the size and direction of the force. So force is NBIL. N in this case is 10. B is 0.5. I is not given, but we have voltage and resistance. So if we know V equals IR, then I equals V on R. So this is 9 on 6. And L, well, it's 9 on 6. And L, the side we're looking for is JK. So this side and that side is 12 centimeters, but we need meters. So 0.12, and this simplifies to 0.9. So direction. So if we look at side JK using the right hand slap rule, so we can see that the magnetic field is going to the right. And if we follow the current, then the current's going into the page. So then if you use the right hand slap rule, then you can see that force will be going down. So the force, since we have to use the directions A to F, instead of, you can't write down here, you have to put a letter, and the letter would be D. So D. So what's the side of the force acting on KL? So KL is actually parallel to the flux field line. So it's going to be 0. And then you have to explain. So you would say side KL is parallel to field lines. I think they also accepted flux, so either way is right, of the magnetic field. So since it doesn't experience magnetic field, no force acts on it. So question 4, we're asked to calculate gravitational strength. So we know, and appropriate unit. So we know G equals GM on R squared. So G is 6.67 times 10 to the negative 11 times M, which is always the mass of the planet. So 1.3 times 10 to the 22 on R squared. So 1.2 times 10 to the 6. And the R, always be careful where it's from. In this case, it's asking for at the surface of Pluto, so we can just use the radius of Pluto. And this comes out to 0.6. And we know the unit's going to be ms minus 2, because you can also call gravitational field gravitational acceleration, if that helps you remember. But you can also try and use units to figure it out as well. But like we kind of know. So 0.6 ms minus 2, and again sig figs. I think they've gone with 1 in the answers, but you could have gone to 2 because all the units, the values we used, the minimum was 2. So calculate the period of orbit of Charon. So this is where we use, once you equate centripetal force and gravitational force, you get this giant equation. And if you rearrange it to find T, you get 4 pi squared on R cubed on GM. And so G is 6.67 times 10 to the negative 11. M is still the weight of the planet, because when you equate these two things, the mass of Charon will actually cancel out. So always make sure you're using the right mass. So it's still 1.2 times 10 to the 22, and R is the radius of orbit. So it's this one. It's no longer the radius of Pluto. And they didn't state that this wasn't measured from the center of the Pluto. So we can assume that it already has the radius in addition to it. So we can just So like if there was ever a question where this value was less than the radius, then you could safely assume that you have to add the radius onto this, because otherwise it would be impossible for the moon to be circularly orbiting inside the planet. So like hint, hint, I guess, if this value is less than this one, that you have to add the radius together. So R is 1.8 times 10 to the 9, I think. I've got 7. And then you chuck all of this into here, and you should get 5.2 times 10 to the 5. Again, sig figs is 2 because of these two values, which are the lowest. So 5.2 times 10 to the 5. So now it's asking us to determine what speed the moon would have to, not the moon, sorry, this so they're replacing the moon with a spacecraft, and they're asking what speed would the spacecraft have to go around Charon if it wants to have the same radius. So if it wants to keep this value here. So for this question, you have to evaluate the 3 options. So this is, I think this is worded a bit weirdly. You don't actually have to go and discuss all 3 possibilities. I think the answers just wanted you to see which one was correct. So in this case, Melissa is correct. Oh, my M looks like N. So Melissa is correct. And then we have to explain why. So this is 3 marks. So I discussed, first I said, as seen in B equals 2 pi r on t, velocity of an object in orbit is only dependent on radius and period. And then where you have to say that t is 4 pi squared r cubed on gm, because like just to further explain that in t there's also nothing about the mass of the spacecraft. So to further explain that, you have to, I would mention that m is mass of the planet. So Charon, not the spacecraft. And then just to like sum it up, you would say as both radius and planet mass wanting to be kept constant, regardless of the weight of the spacecraft. So regardless of spacecraft weight, same orbit will be achieved. Will be achieved if traveling at the same speed. So just to summary is that explain what happens when, or like what velocity is dependent on, and then just expand on that more and show that the mass, I guess, of the spacecraft is not required in any of the equations, and I think that should be sufficient. I think probably here I should have wrote it the other way, like r equals vt on 2 pi, because it's r that we're looking for. Vt on 2 pi. So then continue to explain that t is this, but yeah, the same thing. So calculate, we have a coil here, and it's just, it's a uniform magnetic field. So calculate the magnitude of the magnetic field. So in this case, we have area and we have flux. So we know we're going to use flux equals field strength times A. So B is field flux on A. So that's 0.2 on 0.4 times 0.3, which comes out to approximately 1.67. But we should use 1.7 because, again, significant figures. We only have 2 in all of these. So calculate magnitude of the average EMF in a quarter of a turn. So that's like when it's vertical to horizontal to vertical. So show all the steps. So we know that EMF is N. Since it's asking for magnitude, you don't have to write the negative in front. Yeah, this one, and then N is 10. 10 times, so delta phi would be the maximum, which is given to us, so it's 0.2. And the problem with this question is that we don't know what time is. I mean, we do, but like we have to figure it out a bit. So it says that the coil turns 4 times in a second. So we know that if something is turning some amount of things in a second, that means that that's the frequency. So frequency is 4 hertz. So then T is 1 on F, which is 1 on 4. So it's 0.25. And then, so that's for 1 turn. So if we want a quarter of a turn, we'll have to divide this by 4. So quarter turn is 0.25 divided by 4. So, and then you could sub that value into your EMF. So you get E equals 10 times 0.2 on 0.25 times 4. And then that comes out to exactly 32. And yeah, that fits. I think they accepted 32 to 2 significant figures, even though we only used 4 times in a second. But yeah. So now we have a split ring commutator. I mean, a slip ring commutator, and is replaced by a split ring. So we know when we replace it by a split ring, we have to reverse the current. So if it's reversed, then the voltage becomes positive. So basically you just have to draw the same graph, but modded. So just like this. And that's it. So now we have a power station grid. So calculate the total electric power loss in the transmission line. So this is just P equals I squared on times R, because we have everything we need, because it directly tells you that the current is this. And the resistance in the lines is 3. So 3, so this is 120,000, 1, 2, 4 zeros. But you have to be careful because the answer's in kilowatts. So our answer here is in watts, so you just have to divide by 10 to the 3. So it's 120. So now they're stepping up the voltage to 250 instead of 500. So by what factor would the power loss in the transmission lines increase? So if you remember, if you have like, it's currently, it's going from 500 to 50. So it's going by 10, 500 divided by, 10 to 1. So if voltage goes down by a factor of 10, that means current's going to go up by a factor of 10, because voltage and current are inversely proportional in transformers. So if you look at this question, so they're going to decrease the voltage by 2, which means the current consequently would be increased by 2, because whatever happens to the voltage, the opposite thing happens to the current. So our original current was 200. So I2 is going to be 2 times our original current, which is 200. So it's going to be 400. And then we can just calculate power loss again. So I squared times R, which is 4800, 48 with 4 zeros, and you can just compare these two values. So 120 kilowatts to 480 kilowatts, and you can easily see it's been multiplied by 4, so it increases by a factor of 4. And then if you just think about it, it makes sense because we know that we want to increase voltage in power lines to decrease power loss, but in this case we've decreased voltage, and that's consequently increased current and increased power loss. So you can be sure that your answer is correct because you have a higher power loss than before. So draw all the forces on the rider. So we know it says in the question that it's driving at a banked angle so that there's no sideways friction force, so you don't have to draw that. And then we know there's a weight force and a reaction force. And then we know that F net is going to be our centripetal force, so it goes to the left. So find the angle of banks for there to be no sideways friction force. So we know the equation is theta equals tan inverse v squared on RG. And if you ever forget where that comes from, you can just draw a little triangle of forces. So this is Fn. It's got up, and then this is Fw, and this is Fc, and this would be your same theta as this one. And then if you think about it, tan theta is going to be opposite over adjacent. So tan theta is going to be mv squared on r divided by mg, so times this, and then you get tan theta equals v squared on rg, which is what we used here. So if you ever forget like what the formula is, you can always make it anytime. So theta equals tan inverse of, so we plug the values in, so 10 squared on 20 times 9.8, and theta comes out to approximately 27 degrees, which makes sense because lowest sig fix was 2 in this case. 27 degrees, oh, don't need that. So now we have a car going at the top of a roller coaster, so calculate the speed to achieve 0 normal force. So if we do F net at point P, F net. So point P is going to be a wave force, and there's going to be a reaction force. And because the bump is going like this, then that means Fc is going down. So the net force is down. So that means it's going to be Fw minus Fn. So we have centripetal force is F weight minus Fn. And we want 0 normal force, so this goes to 0. And then we can just equate centripetal motion to net weight force. And then you get V is square root of Rg. And R is 5 and G is 9.8. So you can just put that into your calculator and you should get, R is not 5, R is 6.4. 5 is the distance from Q to P. R is this one. And this comes out to 7.9. And sig fix makes sense because we have to from both 6.4 and G. Anytime you use G, the maximum sig figs you can have is 2 anyway, because G is 9.8. So the car cannot actually achieve the speed because it only gets up to 4. Oops. So calculate how fast it would be moving when it goes to point Q. So here. So we can tell for this question, we're going to use energy conservation and at P and at Q. So EK plus EG equals ES1 plus EG1. Oh, that's EK. So point P EK is going to be half mv squared. The mass is not needed because if we expand everything plus, let's say equal sign, half mv squared, maybe I should call it m1 v1 squared plus m1 gh. Because we're gonna have to consider Q to be the ground level, even though you can kind of tell the roller coaster is gonna go below Q, but for our purposes, we're just gonna consider H to be 0 here because that's the most reliable, I guess. But you would need to assign a H0 value anywhere, so that's probably the best place to do it. And then we don't have mass, but we don't need mass because mass is in every single one of these terms, so we can cancel it out. So yeah, half v squared plus gh is, sorry, this is completely 0, half v1 squared. So v1 is the one that we want. So v1 is the square root of v2 squared, v squared plus 2gh. So that is 4 squared plus 2, 9.8, and h is 5. And that comes out to 10.7, although technically I think we should just leave it at 11 because sig figs again, 11. So now we're at projectile motion. So calculate the height of the ball when it strikes the wall. So in the question, we've been given the mass, the angle of inclination. They told us to ignore air resistance, which makes sense because it's projectile motion, and then it tells you that it leaves the ground level with speed. So that's your your initial speed, but we still have to split it into vector components. And then it says instead of reaching the ground, it strikes wall 26 meters. So we've been given the range, and that's what we're going to use to calculate time. So we have speed equals distance over time, and if we rearrange that, we get time equals distance over speed. So this is, sorry, for the horizontal. We have 26 over 20 cos 30, which comes out to like 1.5 seconds, but keep this value in your calculator. And then to do the vertical component, the only thing we don't know is the velocity when it hits the wall here. So we're looking for the equation that doesn't have velocity, and that's going to be s equals ut plus half at squared. So u is going to be 20 sine 30, and then times your t value. I'm just going to write 1.5 plus half of negative 9.8 times 1.5 squared. Again, use the proper version. And then s is going to be 3.98, but again, sig figs is probably better to write 4.0 meters. And yep, so next question is a continuation. So it's asking to find out what, it's a scientific method question. So control variables are the ones that's kept constant. Dependent ones are the ones that's measured. And let me write these nicely. So these ones are kept constant. These ones are measured. And these ones are changed. So the ones that are kept constant could be either the angle, or so this angle, or the initial velocity. So actually, let's read the question first. So they're keeping the catapult at a fixed angle and it lands at the same height as fired. And what they're measuring is the relationship between initial variables and range. So from this part, you can see that range is going to be the one that they're measuring. So the dependent variable is range. And the one that they're changing is going to be this one. So initial variables is going to be initial velocity because they've kept the angle the same. So initial velocity, and then the angle is the controlled one. So now they have given us some data, and we're gonna have to graph it, but be careful you read everything because they want quite a couple of things. They want the scale and the units, and they want uncertainty bars only for the range, so only for the in the vertical direction. And they want a smooth curve. So curve is important because usually we're used to drawing like straight lines for best fit, but this time they want a curve. So if I plug, so first you have to determine your scale. So if you look at the values they've given us for the range, it goes up to 2.15. So you probably want from 0 to 2.5 or something like that. And then initial speed is quite simple. It just goes from 1 to 5. So 1 to 5 would be a range. The easiest way I found is to graph or determine a scale using like pre-given boxes is just to count 5 at the bottom, or in this case count 2 because it's quite small. So 2, sorry, not count, just like put lines so you know how much there is. So we have 2, 4, 6, 8, 10, and 11 boxes. So since we only want 1 to 5 at the bottom, it would be really easy for us to just do 1 to 5 with 2 boxes in between. And then the vertical one, there's quite a few boxes, so you might want to draw a line every 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5, 1, 2, 3, 4, 5, and then the top would match. So as I said before, we're looking for a range of 0 to 2.5, and conveniently we have 5 lines, so we can easily go from 0.5, 1, 1.5, 2, and 2.5. And then so we've done scales. The next thing is units. They've already given us the units. It's meters and meters per second. So we just have to put meters and meters per second. And so we've done this whole dot point. And now we have to do uncertainty bars for the range. So if we start plotting our data, we have at 1, it's 0.1, and then at 2, it's 0.35, so it's approximately here-ish. At 3, it's 0.78, so this is 8, so 7, 8 is kind of here. And then at 4, it's 1.4, so 4 would be 1.4 here, I think. And then at 5, it's 2.15, so 2.1, 2.15. And then to find out uncertainty, look at the range values given. So you can see they're to 2 decimal places. So the uncertainty is going to be in the last one, the last decimal place. So the value of uncertainty would be the plus or minus half of the missing decimal point. If that makes sense. So this is 2 decimal points. So the third decimal point would be 0.001, or like there would be another value here. So the uncertainty would be plus or minus 0.005. It would be half of this decimal point. So it would be half of 0.10. So 0.005 on these on this table would just be half of one of these. So because this would be 0.1. So half of it would be 0.000005. How many zeros am I adding? Nope, sorry. It's just going to be half of one of these boxes. So just up and down by half. Just be careful where the values are, because sometimes they might look like they're at halfway, but they're not. So now that we've drawn the uncertainty, we just have to draw a line of best fit, and it has to be a curve. So if I go like this, that's wrong. Don't do this, because The thing with the uncertainty is that your line of best fit has to go through the uncertainty. It's a bit hard on the iPad, but basically, this line has to go through, like it has to go through this section here. It can't go like this or like this. It has to intersect that point. Because normally with lines of best fit, like you'd have like dots here, and it just goes like in the middle. It doesn't have to touch them. But since we're drawing uncertainty bars, it has to go through the uncertainty. Yep, and that's it. And I think in this case, they actually allowed us to extrapolate the graph behind it. So I think they allowed us to go back to 0. But usually we're not allowed to do this. So yep. So we have a relativity question now. So length of a spaceship is measured to be exactly 1/3 of its rest length. So L is 1/3 of L0. And then what's the speed? So if L is 1/3 of L0, and we know that L is L0 on the lens factor. So lens is 1 on lens is 1/3. So lens is 3. And then to figure out speed, we know that this is 1 on square root 1 minus v on c squared. So 1 on 3 squared is 1 minus v on c squared. So v on c is square root of 1 minus 1 on 9. And that comes out to 0.94. Yeah, sig figs here, it depends what value. No, it doesn't really matter what c is, I guess, because we're just finding the fraction. But because they worded it, they said 1/3. I think we can use 2. So more relativistic stuff. So calculate the lifetime of the particle as seen from the scientist frame of reference. So if we scan the paragraph for things seen by the scientists, it's that they see them travel 9.14 meters. And then we're also given the speed. So we know that speed equals distance over time. So time equals distance over speed. And just remember that all of these values have to be ones that are measured by the scientists. So we have 9.14 times 10 to the negative 5 divided by 0.99875 times the speed of light. And that comes out to 3.05 times 10 to the negative 13. We can use 3 significant figures this time because of this value here, and this one has a much higher amount of sig figs, but we have to always use the lowest one. So calculate the distance that the particle travels as measured by the particle. So this time, okay, so since distance is at rest relative to the scientist, so if we're asking for in the particle's frame of reference, then we're looking at L, not L0. So L is L0 on lens. And then L is, so they measured it at 9.14 times 10 to the negative 5. And then they gave us lens was 20. And then that comes out to 4.6 times 10 to the negative 6. I used 2 significant figures because the lens was given to 2, and I used that one. So explain why scientists would observe more particles at the end than classical physics would expect. So if we're expecting more particles, you have to explain that. So this is in the frame of the scientists. So for maybe in the scientist's frame of reference, time dilation occurs, causing them to see the half-life of muons as longer than observed by a muon. So that's proper time. And then you have to link that to the question. So then as they seemingly exist for a longer time before they decay, they are able to travel to the end of the laboratory, or like travel to the end. More, maybe I should write more of them. So more of them are able to travel to the end than expected in classical physics. So for this question, you just have to explain that the scientists have time dilation, so muons might only live for like say half a second, but for the scientists, they'll live longer than that. So for the scientists, it'll look like they have more time to get to the end. So like a muon actually might like decay when it hits here because of the time, but for a scientist, it might be able to live until it goes way past here. So that's why it looks like more of them are able to hit the end of the laboratory. So now we have a momentum conservation question, except it's asking for inelastic or elastic. So to determine this, we just have to compare the kinetic energies. So kinetic energy before is half m1 u squared plus half m2 u squared, which is half times 4 times 5 squared plus half times 2 times 2 squared. So it's 54. And then kinetic energy after is, so since they're connected bodies after the collision, we can consider their weights together. So half m1 plus m2, and then v squared. So half 6 times v squared. But we actually don't know what v squared is here yet. So we have to use conservation of momentum to figure it out. It's probably best to do this step like before maybe, but you might not realize that you're missing velocity. But yeah, it doesn't really matter as long as you can show working out and show how you got the answer. So if we're doing momentum conservation, is yeah, so m1 u1 plus m2 u2 is m1 plus m2v. So 20 plus 4 is 6v, and then v is just 4. And then you sub that into here, and then you get 48 joules. So then you have to say inelastic, because the initial kinetic energy is not the same as the final. So now we have a springs question. So determine how far the spring stretches until the mass comes to momentarily to rest at the bottom. So momentarily to rest is it's a bit tricky because it's not actually asking for when Fs is equal to F weight. It's not asking that because it's only asking momentarily at rest. So it could be, so since it's falling, it's like it reaches the bottom and then it oscillates between these two places. And it's asking these two places. That's an ugly bracket, but it's asking for the total extension at this place. So it's not actually when the mass is at rest. It's just when it's at its lowest point, because then at that moment it's momentarily at rest, because then it has to go back up. So instead of letting the weight force equal the spring force, we're going to use energy conservation. So we're going to let gravitational energy equal the spring energy. So mgx, mg of the extension equals, mg of the gravitational equals mg of the extension. And then 2 times 9.8 is half times 20 times delta x. In this case, I canceled the delta x's from each side. So delta x is 2 times 9.8 divided by 10, which comes out to 1.96. In this question, technically, I think you'd have to write 2.0, but I think they let you get away with 1.96. I was thinking 2.0 just because of the G, which we used was 9.8. So explain the 3 energies involved and the total energy of the mass vary, and the total energy of the mass vary, or how the mass varies as it falls from top to bottom. So this is a bit of a trick question because of this part, but I'll explain that in a bit. So first we have to explain the 3 energies. So Eg, which is gravitational potential, is highest at the top and lowest at the bottom. And then we have Ek, so kinetic, is 0 at both top and bottom, and max in the middle. Maximum in the middle, and then the third energy type we have is Es, is 0 at top and max at bottom. So the total energies part is the tricky part because it's asking for total energy of the mass. So out of these 3 energies, only Eg and Ek are total energies of the mass, because Ek is energy of the spring and not the mass. So when we're discussing this last condition here, you have to say that E total of Eg and Ek decreases from top to bottom. So don't be confused into saying E total is constant or stays the same, because we're not including Es. So E total does change, and if you're confused about whether it decreases or increases, consider that Es, which is the one is missing, goes from, so at the top, bottom, so it goes from 0 to a high number. I'll just call it infinity. It's not actually infinity, but I'm just trying to demonstrate that it goes to a high number. So if the total energy is kept constant and E total is increasing, I mean, Es is increasing, and so E total is like this, Es is like this. So we want, maybe I should draw like a mini graph. So E total, we want to be a flat line. Es we know is increasing. So we want to add something to this graph that makes it a flat line. So you can see that what we want is a decreasing graph. So that would be Eg and Ek. So that's why the total without Es should be decreasing. So now we have some light rays and we're doing some reflection. So find the critical angle. So we know the formula for the critical angle is sine theta c is n1 on n2. And we derived that from, because theta was going to be 90 for the other sine values. So c is going to be theta c. Sine inverse of 1 on 1.44, which is approximately 44 degrees. I think we could have used the last significant figure because we've used 3 here and 3 here, but yeah, that's fine. As long as you have a considerable amount. So now it's asking to draw the rays that are possible when the angle of incidence is less than the critical angle. So there's 2 options. We could have what we would expect, which is refraction. So it just leaves to the other side. It doesn't go back. But the other one that I think the examiner report said that a lot of people were missing was that it goes back into the glucose, so total internal reflection, IR, and those were the two options. So now it's saying that the angle to the normal is a value greater than the critical angle. So an observer at point X says that she can't see the laser. So just as with the other question, so the possibility, if she's not seeing it at X, then the only thing that could have happened is that it's gone into the glucose solution. So you would have to explain total internal reflection has occurred. So total occurred. The laser is reflected back into glucose, and then just say that hence that's why. Hence she cannot see it at point X. Point X. So now we're doing some wave stuff. So there's a sound wave at 680 hertz, and we're given speed of sound. So calculate the wavelength. We're just going to use the wave equation. So lambda is v on f, which is 340 on 680, which is 0.5. So now there's a diagram, and we have two loudspeakers, the sound in phase, 7 students here, and then it says that student in the middle is the same distance from both speakers. So you can see this is very similar to the double split experiment, but we have 2 loudspeakers. So this would be the distance between the slits. This would be the distance from the slits to the wall that's being reflected on. And you can see this is like fringe separation almost. But we have to keep in mind that it's not the double slit experiment because we're dealing with sound here. So Eli says that they will hear similar sound of double the intensity, and then another student, Sam, says that it will depend on where you are. So we know that Sam is correct, Eli is not, because the interference of the sound waves could either be constructive or destructive. So Eli could be correct if it's constructive, but he doesn't mention the destructive interference. So start by saying who's correct. So Eli, oh sorry, it's not Eli, it's Ellie, is incorrect. Sam is correct. Sound waves will interfere. So maybe destructive or constructive, depending on position of the student. And then therefore Ellie is always correct. And you might also want to mention something here about that's what happens when you double the, like, that's how you would get an increased intensity, just because it's 3 marks, and yeah. And then maybe also explain destructive interference and how then that would result in a lower intensity. So with students 2 and 5 hear similar sounds or different sound intensities. And if you predict one will hear a high one, which one would it be? So students 2 and 5 are these 2 kids. So as you can see, they're already a different distance apart from the middle. So we can assume that they won't hear the same. So first we'll figure out what delta x is, just in general. It says delta x fringe spacing is lambda L on D, which is half times 24 on 4, which comes out to 3. So if we consider 3 is the 3 is the the fringe spacing between two what do you call them? Sorry, I forgot the word. Two bright spots, or in this case, two spots of constructive interference. So that means if the students are 1.5 meters apart, then since this is going to be 3 meters apart, then this is going to be a bright spot. This is going to be a bright spot. The next 3 meters will be a bright spot because fringe spacing from the middle should be bright spots because the same ones, the same distance apart. So if 2 is a bright spot, and then the ones in between, they're going to be the dark spots. So now we can see that 2 is going to be constructive interference, and 5 is going to be destructive. So we know that student 2 here is a higher intensity due to constructive interference, and student 5, student 5 here's lower intensity due to destructive interference. And yeah, so now we're talking about standing waves. So there's a string of length 4 and it's fixed at both ends. So it's going to be like this. Oh, it's going to have the same type of node on each side. I mean, it's going to have a node on each side. So speed of waves is this, calculate the lowest frequency. So we know the formula is lambda equals 2L, and L is 4, so in this case it's 8. But if you ever forget how to do that, you could always consider a string that's closed at both sides, and you know you have to have a node at each side. So if you need a node, then the lowest, like the smallest, I guess. So we want the lowest frequency, so we want the biggest wavelength. So the biggest wavelength we could have is this one, because if you draw like more, so this is the wavelength now, but in this one, this was only half the wavelength. So you can see having the lowest amount of like packets gives you the highest wavelength. Oh wait, this diagram might make you confused, but so in this case, lambda equals 4. I mean, yeah, but in this case, half of lambda is 4, so the lambda is 8. So that's why you want this one, because the highest, so you want the highest wavelength, because that corresponds to the lowest frequency. So that's why this scenario is the one you want. And then if you ever forget this formula, you can just consider that the string is 4 meters and it would look like this, and one packet is half of a wavelength. So then 2 packets would be a wavelength. So then the lambda would be 8 meters. So calculate the frequency of the second lowest. So first we need the frequency of the first one. So that's B on lambda. So 240 on 8, which is 30. And then the second one is just twice the first one because we have a string that closed at 2 ends. So we don't only look at the odd ones. So that's 60. So next question is to explain the physics of how standing waves are formed on the ring. So I started by talking about the requirements of the 2 waves, but I don't think the answers did, but I'll just write what I wrote. So we need 2 waves of same wavelength, amplitude, and speed, travel in opposite directions to each other, and reflect at ends of the string. So because it's asking about the string here, so we're still talking about this the previous parts of the question, so we know we're still talking about a string closed at both ends. So then overlapping and interference causes creation of a standing wave. And yeah, so question 17, now we're doing the photoelectric effect. So what is the cutoff potential of a light at 6.25 hertz? So EK max is equal to EV0, which is equal to H times delta F. So V0 is just H times delta F. Saying delta F here in the answers, I think, really emphasize this point is because I think, I'm not completely sure, but it's because you're doing, the blue light is doing work on the sodium, so you don't want like the overall work. You want the left, like not leftover, but kind of here. So that's why we use minus, and then just put H there, and then 6.25 minus 5.50 times 10 to the 14, and then you get 0.31. And again, I think you could have used one more sig fig because of the values we've used, but I think they just wrote it to 2 in the answers. So on the graph, sketch the curve if it has ultraviolet light with a higher intensity than the original one. So if we remember, so if it has a higher intensity, then the photocurrent is going to increase. We don't know by how much. It's not, they don't like say it's doubled or anything, so it just has to be higher than the original one. But since we're also changing the light to ultraviolet, and we started with blue light, and now we're using violet, I think. So this has a higher frequency, I think, if I'm remembering how it goes. So then it would have a lower stopping voltage. Does that make sense? Maybe. Yes, it does, because negatively it increases this way. So outline 2 results that's not explained by the wave model. So there's the threshold frequency, which is not explained. So you can say that the wave model predicts any wave. My handwriting. Wave model predicts any wave can emit an electron. And then talk about like what the reality is. So I wrote what reality is only waves with frequency higher than the threshold frequency can produce a photocurrent. So producing a photocurrent means ejecting an electron, but I just didn't want to repeat the same thing. So the other thing that it affects is stopping voltage. So wave model predicts increasing intensity. So I'll just write it in shorthand. Increases the work or energy done to the metal, and hence produces a higher kinetic energy for each electron for each ejected electron. electron, but we know that's not true because intensity only affects the photocurrent, or how many electrons are ejected, and not the kinetic energy of each one. So reality is that intensity, so then we have to mention stopping voltage here. So ejected electron subsequently increasing stopping voltage as well, because if you're increasing EK, then obviously you have to increase VO. And then the reality, or what they found in the experiments was that increasing intensity only increases number of ejected electrons and photocurrent. So photocurrent instead of the stopping voltage, which is what the wave model predicts. And answers also had one more thing that you could have written, but you only had to write 2 of these to get full marks. So the other thing that you could have written about was negligible time delay. So they said that the wave model predicts that if the intensity is lowered, then a measurable amount of time delay between when the light hits, so the illumination of the metal, so when the light hits the metal and when you can observe, then so delta T will exist between illumination and observation of photocurrent. But in reality, the experiments showed that there is no delta T regardless of I. So the last point was just that another thing that the wave model said is that there'll be a bit of delay if the intensity is lowered like to a certain point. There'll be a bit of delay between the time it takes for the so as soon as the light hits the metal, there'll be a bit of time taken before you can actually observe a photocurrent. But experiments showed that there actually isn't a delay, and that no matter how low I you go, it'll always be pretty instantaneous. So question 18, draw an arrow demonstrating the atomic energy level resulting in the emission of 1.65. So we have to find the energy level that corresponds to this. So the easiest way is just look at the n numbers. So we have a 5 and a 5, so it makes 0. So you can see it goes from here to here. So what is the shortest possible wavelength of photon that can be emitted when n equals 5 to the ground state? So the shortest possible wavelength of a photon is actually the one that releases the most energy. You can see in the equation equals hc lambda. So if we want lambda to be really small, then E is going to be really big. So we're looking for the largest energy. And the largest energy would obviously be all the way to the ground state. So if we use that value, we have let's rearrange it to find lambda first. So lambda is hc on E, and then E is our the largest value for energy loss. So it's 3.75. And that comes out to 331 nanometers. 331. So student observed a spectral line corresponding to 2.5, and then in terms of the quantized states, explain why it would be impossible. So 2.5, if we're looking for a difference of 2.5, we cannot find one. And that makes sense, given that it's asking us to find why it's impossible. So for 2 marks, you would have to say that first, explain that only energies corresponding to energy differences between energy levels can be observed. Or you could write can exist. That'd probably be better. So can exist. So that's like a general statement explaining just the theory, and then you have to apply to the question. So then as 2.5 electron volts does not match energy level difference seen in figure 17, or like you can write the hydrogen, oh sorry, is this hydrogen? No, sodium emission spectrum or something like that. Just explain like how you're basing that there isn't a difference. So since it does not match an energy difference seen in figure 17, and then just say it cannot exist. And hence it's impossible. So question 19, last question. So Roger and Mary are discussing diffraction. So Mary says electrons produce diffraction pattern. We know that's right. And then Roger says this is impossible because it's a wave phenomenon and electrons are particles. And diffraction can only be observed, blah, 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 with waves and light. So we can easily tell that Mary is correct and Roger is wrong. Roger is incorrect. So it's asking, I think the question's worded a bit weird. So it's asking to describe two events that show the difference between Mary and Roger's views, but the answers actually only wanted you to explain why Mary was correct. Like you didn't have to show that Roger was, you didn't have to like show something or provide an experiment where electrons didn't act as waves. So the questions, or maybe it's the answers, but like you didn't have to write that much. So they just wanted you to explain why is Mary correct. So I started off by saying electrons can display wave properties. And then it's asking for two experiments. So the two experiments I chose were very similar, but they accepted both of them. So I chose the single slit and the double slit experiments. So electrons passing through a slit will diffract. Similarly, when passing through two slits, resulting diffracted waves diffracted waves will interfere constructively and destructively. And then to like sum it up, you'd say since diffraction and interference wave properties, these experiments like support. You never want to say prove in science because they'll mark you down for it, because I think our school teachers told us that you can't prove anything in science. So just never write the word prove. You want to write something like suggest or support. Suggest that electrons, so the question was asking, can they produce a diffraction pattern? So we've already said that they can diffract as they can act like waves. Act like waves. So, waves. And yep, that's it.